to the new blank sheet to have them, because we will need them both. So provide me the time. So this is one equation, and the other equation would be insofar we have only those two equations that are unchanged. So now I would do the trick and apply a vector product on both sides with the nabla operator. So I will leave this intact, and this, I mark my line here, would be somehow changed. So now I would have can't see much improvement possibly. Well, okay, that's true, but now let's somehow change the equations. We have too much variables. We have flux density and intensity of magnetic field. We have electric flux density and electric field strength, which is a kind of intensity of electric field. So let us try to get less variables here. We would be able to do that if we impose those material constants. So let us decide that we would have their intensities, that is electric field strength and magnetic field intensity only. We can do that by inserting something here. So this in fact is electric conductivity plus times electric field strength plus the time derivative of a product of permittivity and electric field strength. And here downstairs we can replace magnetic flux density by a product of permeability and magnetic field intensity. So this could be also written like minus time derivative of mu h. Now there is a short story to be presented. We have a time derivative of a product, mu times h. So, according to the law of mathematics, this time derivative can be obtained like a time derivative of mu times h plus time derivative of h times mu. Generally, we have to consider that both mu and h is a function of time. But fortunately, we have made the rule that we only talk and describe the problem today on stationary media. If a media is stationary, it directly implies that its property does not depend on time, and therefore the time derivative of mu is 0. And therefore we can change the order. We can write minus mu time derivative of h. Now the same story I should now tell you about this point when we have the time derivative of a product of permittivity and electric field strength, and therefore just noting that we have linear, stationary, homogeneous and isotropic media, we could rewrite that. So I will do that for the second equation again. Now the right hand side of this equation reads nabla vector product with mu time derivative of h against time derivative, and we have minus here. And provided what a nabla is, it is a set of space derivatives, so there is derivative of the function against x, y and z in Cartesian coordinates, and provided that mu does not depend on the coordinates, so it's the same at all places, which we call homogeneous, we could shift the constant out of this equation. So if we had the homogeneous media, we could write that this is minus mu nabla vector product now being investigating homogeneous, stationary, isotropic linear media, we can also change the order of differentiation. This is a differential operator, but we can, in that case, change the order of differentiation so that we can get the time derivative before the nabla operator. So we now can write it this way: minus mu the time derivative of nabla vector product with h. Well, and this is an important point. We still keep that this left-hand side of the equation is equivalent to the right-hand side, based that the media is isotropic, homogeneous, and so on. And we now have found out that this is this. So we can substitute the inside of the bracket by the right-hand side of the first equation. Okay? Let us do that. So we have on the next paper the left side, nabla, vector product nabla, vector product electric field strength, as equivalent to, let's put it down, and what we have done. Well, we had time minus mu time derivative of a bracket, so let's put it down. And now what is in the brackets? There is the right side of the equation 1, which is electric conductivity times electric field strength plus a time derivative of a product of permittivity times electric field strength. Well, what's nice about this equation, there is only one variable, that's the electric field strength. And therefore, we have simplified the equation. We had 4 variables at the beginning, and now we have only one variable, the electric field strength, within this equation. Now we have to do some tiring work according to standard rules of mathematics so that we can reformulate the right side, providing that the media is linear, homogeneous, isotropic and stationary. We would be able to get this conductivity over here and the permittivity again over here, and we would get something like so we have now minus mu sigma, the first derivative of electric field strength against time, minus a second term, minus mu epsilon, second derivative of electric field strength against time. We are close to done, but still we have to do something with the left side of the equation. It seems to be quite tricky. Couldn't this be simplified? Yes, and the reply is yes. Nabla, vector times nabla, vector times a vector simplifies to gradient divergence of the vector, which in a source-free medium is 0, minus Laplace operator applied on that vector. So what we have here is minus Laplace applied on the electric field E as this. Let us get this equation. Again, this simplification is possible whenever there is free space with no source of the electromagnetic field. So this is an equation that governs propagation of the wave, not creation. And now let's rearrange that to a final class of wave equation in electromagnetics. It looks like Laplace E minus mu epsilon second derivative of E against time minus mu sigma first derivative E against time, and the result is 0. Now this is a wave equation